Hello, good morning, everyone. I'm really very happy to be with you today. I'm sorry for this recording. I had some priorities today, so I thought to record this lecture for you to be with you for today. Tomorrow, inshallah, it's going to be Thursday, and I will give also a live lecture in the campus, and we will be together tomorrow, inshallah. But for the time being, I wanted you to catch up with the linear transformation. So let's start. First of all, it's my pleasure, as I told you. This is week number 4, and this is lecture 2, the end of the linear transformation. Once more, our exam will be after 2 weeks. The next week, we will take Lintoff application. So I want you to study hard, and this part is really very important. I'm Dr. Omar Salah, as you know, and I'm going to be with you. All the recorded lectures and everything, you will find them on my YouTube. And also, at the time being, please do visit Moodle frequently and go to Moodle. It's the big day. You will find the mock exam over there. You can access it and try to download WiseFlow first, then try to access this mock exam on the midterm. All the questions will be available for you once you will be able to answer all the questions once we finish our lecture today and the lecture of the next week, inshallah. Okay, what I want to start with is I want you to remember that linear transformation conditions are really very important. We understood how to do a transformation, moving stuff from R2 into Rm or vice versa. And there is a conditions for this transform to be linear transform. The conditions for a transform to be a linear transform are really very simple. All you have to do all you have to do is to be sure that of the following two conditions. The first of them, as you know, if we are making a transform T that moves stuff or vectors or whatever from Rn into Rm, in order to be a linear transform, the transform of the addition of the two objects in Rn should equal to the transform of every one of them separately to separately. So mainly, once you get the summation of the two vectors first, then you do the transformation. It's going to be exactly the same as transforming the first vector, then transforming the second vector, and adding them together. That's one of the conditions of the linear transform. Also, linear transforms keep or reserve the multiplication of a constant or a scalar. So just getting a transform of a constant vector times constant value times a vector will be exactly the same like getting the transform first for the vector, then multiplying by a constant number. And that's for every a belongs to R and for every u belongs, of course, to Rn. I want you to, I want you all to understand that T transform from Rn into Rm. This is all we already mentioned previously in the last lecture. So it's really very important for you to study first the last lecture, then to go through this one. And as I told you, I will go with you tomorrow in overall about linear transformation, inshallah, on our live lecture in the campus. So T transform of k times u, it's going to equal to k, the constant value, times the transform of this vector, as you can see. Also, the transform of the 0 of Rn will be mapped. Mapping, it means after transformation. It will be mapped into the origin of Rm, as you will see. These linear transformation main conditions are really very important to remember and to keep in mind in all times. Okay, let's do a quick problem. This exercise, first of all, consider the transform which moves stuff from R3 into R3. Okay, how this transform is going to work? It's going to work simply as you will see. For the input vector, which consists of x, y, and z, it will be mapped into 2 of y, first component, x, then minus z for the third component. And that's for every x, y, and z belongs to R cube, which means the input of this vector. So it will start with the vectors in R3, and it will end by the vectors in R3 after this transform. So look closely to this transform. Okay, if I want to have the matrix of the linear transform as we saw in the previous session, it's very, very simple. I can do it by two ways. The first of them, I will talk about the one that's not here in this slide, but I've already mentioned in the previous lecture. I can start with, instead, this is the first component, or those are the components after the transform. I will start with the first component, but I will write it with all variables, with the same order in the input. So it's gonna be an x, 0x, plus a 2 of y, plus 0 of z. That's the first component. And that will give me the first row, which is gonna be 0, 2, 0, as I told you, 2, and 0. That's the first row in the linear transformation matrix. Then I will go to the second component, which represents the second row. The second row will be, once more, 1 times x plus 0 times y plus 0 times z. So the second row is going to be 1 double 0, as you will see. The last row, the transformation matrix, it's going to be 0 times x, 0 times y, negative z. So the coefficients will be 0, 0, and negative 1. I can do that exactly the same, but with using the columns of a unit matrix of this order. So the first column of a unit matrix is 1 double 0. So all I have to do is to transform, is to substitute the objective function after the transform with 1 double 0. Let's do that. I will start with the first component. Remember, x is equal to 1, y is equal to 0, and z is equal to 0. So once you start substituting in the first component, it's going to be 2 times 0. Once we go to the second component, once more, I'm using 1, 0, 0. It's going to be 1. Then going to the third component, substituting by 1 double 0, it's going to be 0. So all I'm doing is, instead of having x, y, and z, we will use 1, 0, 0. I will use 1 double 0, 1 for x, 0 for y, 0 for z. And I will use these three components and substitute in this bracket by the same order given to you. And you will have the first column. So the first method, it will complete the transformation matrix row by row. But here, using the unit matrix, it will complete it column by column. So the first column is 0, 1, 0. I'm hitting the second column. So I will use 0, 1, 0. 0 for x, 1 for y, and 0 for z. And I will use these three coordinates once more and substitute in 2y, x, and the negative z. And the result will be 2 double 0, as you will see. And those are the values of the second column of the linear transformation matrix. Coming to the last column, I will use 0, 0, 1, and I will do exactly the same, substituting in this matrix, in this function, or in this transform, by the order x equal to 0, y is equal to 0, z is equal to 1. This is what we get. So simply, that's, as I told you, that's the linear transformation matrix that we spoke about. Now I have it, and of course we had a couple of examples, even though this example in the previous lecture once more. We can expand any linear transform or transform be mainly the linear transformation matrix times x, y, and z. That's the input. So if we put the transformation matrix and we use x, y, and z, whatever you do, you will have the image, or you will have the values of the input vectors we saw previously. Also can be written in this form, and it was explained in the previous lecture. So that's mainly the linear transform, which is the linear transform matrix times the input column, which is X, Y, and Z. Okay, very good. Notice that. Just also stressing on the fact of a linear transform. So for example, if I want to transform 2, 4, and 6, this vector, 2, 4, and -6, I'm sorry, all I have to do is to take the transformation matrix and multiply by the input vector, which is 2, 4, -6. Okay, here we go. So now, if we multiply the linear transformation matrix by the input vector, which is 2, 4, -6, it means we will see the result by the idea. Same values will happen when you replace y with 4, replace x with 2, replace z with 6. And that's what you are going to get. So if I used these values and even substitute in the main transform, this is the values that I will have. It's exactly like multiplying the linear transformation matrix in the input column. This example in specific for this transformation, I want to show you also that the results, which is 8 to 6, can be rewritten as 2 times, as if I'm taking 2 as a common from all of these values. So it's going to be 2 times 4, 1, 3. And it is similar to multiplying, getting a vector which is 2 times something, which proves the first relation of the the linear transform operation, as I will see, as you will see together. So once more, we have 8 to 6. This is not the main steps that I will do after that, but I wanted here to point out that I can, if we take 2 out of the result value after the transform from all the components, like 2, 4, 1, 3, it's going to be similar to have the 2 times the transformation matrix, but instead of having the vector 2, 4, -6, it's going to be 1, 2, and -3. So the same value goes here, which completes the first or one of the requirements of a linear transform. The second requirement of a linear transform is the movement or the transform of a sum of two vectors is gonna equal to the transform of the result of their addition. And this is also really very simple. Instead of having 2, 4, -6, which after transform is gonna be 8 to 6, I can distribute these values for any two values that you can think of. So instead of having 2 to 6, I can get 0 to 0 and 8, 0, 6. So instead of having this vector, I can rewrite this vector as any two vectors. One of them, I've choose to make it this vector equal to the sum of these two vectors. Remark, 8 plus 0 is 8, 0 plus 2 is 2, 6 plus 0 is 6. I've chosen these two vectors randomly. I want to see if I get the pre-image of this vector or the value of the vector before transform and added the value of this vector before transform together, is it gonna be the same or not? Okay, once more, here's the transformation matrix, and that's the vector, the input vector. And we did that previously in the last lecture. That's the input vector relative to 806. If you add 2, 0, 0, 0, 4, and -6, you will have your input vector, which is 2, 4, -6, and that's complete the proof. That's T of any sum of two vectors equals the transform of the first plus the transform of the second vector, which means the first property of a proposition of a linear transform is already here, and the second one we already proved previously. And for the last one, it's very, very obvious. If you want to get the transform of 0, 0, 0, it will be transformed also into 0, 0, 0, and so it is exactly the same. So bottom line, this transform is a linear transform. This is how to prove a linear transform. Okay. This is the same slide once more, reinforcing the same idea. That's the linear transformation, okay, which moves stuff from R3 into R3. So if I wanted to check that the transform of 2, 4 minus 6, it's exactly like the transform of 2, but instead of 1, 2, negative 3. It's going to be exactly the same, multiplying this value by 2, 1, 2, negative 3. And the result will be the 2 outside. I can do that in multiplication of matrices. Then I will multiply these two matrices together, and it will give me 2, the transform of 1, 2, negative 3, which proves the idea once more. It's a linear transform. For having 2, 4 minus 6, I can separate these values to be 2, 0, 0, then 0, 4 minus 6, as you can see. Okay, the sum of these two vectors, it's exactly the same. Getting the linear transform of the first plus the second, we know from matrix multiplication and distribution on addition is going to be the same. So you will end up having the same conditions for having a linear transform once formed. That's for number 1 and for number 2. And as I told you, for the third proposition of a linear transform, it's very, very simple. If you insert 0, 0, 0, the value of the transform will be 0, which means the 0 of the input plan or space, as we will see down the road, is going to be mapped into a 0 of the image after that. In this example, he asks you, how can we find the transformation matrix of the linear transformation R3 into R2? So this transform moves stuff from a 3-dimension into 2-dimension by this manner. So you will enter values of x1, x2, x3, and it will be mapped into just only two components, the first component and the second component. The first component is x1 minus 3x2 and 2x2 minus 4x4, 4x3 for all x1, x2, x3 belongs to RQ. I will start step by step. Okay, let's do it first. The transformation can be really very easily written. We will write x1 minus 3x2 plus 0x3. We will go for the second row, 0x1 plus 2x2 minus 4x3, in which I can take the coefficients, which is going to be 1, negative 3, and 0 for the first row. And for the second row, it's going to be 0, 2, and negative 4. Here we go. That's the linear transformation matrix. And it is relative times x1, x2, x3, which is exactly the same. I can do exactly getting this matrix once more by using the columns, okay, of a unit matrix from the input dimension. So if I used 1, 0, 0, okay, if I used 1, 0, 0 for the input vector, once you try to substitute in this transformation, the result will be 1 and 0. If I used 0, 1, 0 in this transform, the result will be negative 3 and 2, and that's at the second column. If I used 0, 0, and 1 in this transform, the result will be 0 and the negative 4, as you can see. So it's really very obvious that we can get the linear transformation matrix, as we spoke, more than one time by using either the columns of a unit matrix 1 0 0 0 1 0 0 0 1 by the input dimension and getting the columns one by one, or write the transformation if it was given to you, both the vectors, both the components x1, x2, and complete with the missing, with taking into consideration that the coefficients is equal to 0. It's really, really very easy. I need you once more to go through the previous lecture, very good, and then try to resolve these problems using a pen and paper, and then go once more for this transform. For this transform, you will find it really very easy. Once more, for a proposition, he's saying to you that a linear transformation E that moves stuff from Rn into Rm. Okay, it's gonna be injective. What's the injectiveness? Injective, if and only if the kernel of t is equal to 0. That's the condition for a linear transform to be injective. So once more, condition for a linear transform to be injective is that the kernel of the transform, the kernel of Rn will be mapped into 0. Surjective, it means if and only if the range of t is equal to Rm. What's the range of t? It's the value of all the vectors that will be transformed using this linear transformation into Rm. It will be contained in Rm without missing point. For the details of the definition of injective, surjective, and bijective, I I found that it's really very good placed just to introduce these expressions for you. By injective, we means no two different vectors go to the same point. Once more, injective, it means no two different vectors go to the same point. It means that each vector will go to a specific point. Surjective covers the whole target space. That means for transform to be surjective, means it will cover the whole target space. So all the images from Rn will cover all the values in Rn. Okay. Bijective, it means it's one-to-one and onto. Also, I want to add that in injective, it is one-to-one, and in surjective, it means it's onto. Bijective, it means perfect one-to-one correspondence. That means both injective and surjective at the same time. Okay, very good. I wanted also to take the opportunity to go through these definitions in depth. Injective, one-to-one, but briefly, because it has a lot of meanings inside and there is a lot of explanations. We will get back to it down the road, but for the time being, it's enough the explanations that you will see. Injective, which means one, it means a linear transformation T such that from V to W is injective if different inputs, it means the values of V, always mapped into different outputs. So you will never find an output containing two sources from V. No. Once more, if different inputs, if you have values different in the input, will be mapped into different images after the transform. In other words, the transform of V1 equal to 2V2, so two transforms will be equal together just only if V1 is equal to V2. It means every vector will be mapped in just only one image. The key point here, the kernel or null space of T is only a zero vector. I'm sorry that we hit this meaning, but we will need it, inshallah, after the midterm. Once we go to vector spaces and subvector spaces, we will be encountered with these definitions once more. Geometrically, no two vectors from the domain collapse into the same vectors in the codomain. So you will never have two sources or two input sources that will be mapped into just only one image in the codomain. Okay, what's the surjectiveness mean? Surjective means that's a transform from V into W. Every vector in W is the image of some vectors in V, which means that W is completely covered by the inputs. In other words, the range of T equals the whole codomain, which means all the vectors of the vectors after the transform covered completely by the sources. So the image of T, the image of transform, covers all the vectors in W. Okay, there are no missing vectors in the output space. So you will never find a value without a source in the main. Bijective, it means both injective and surjective. So it has an inverse. So for a linear transformation to have an inverse, that's the intro, or this is why we did go through these definitions, okay, without being injective and surjective. So it has an inverse, which means T is such from R2 into R3, or from R3 into R2 into R3, and so on. So T of X and Y, it's gonna map in Y of X as an example of having a bijective and surjective at the same time transform. I think this idea completes the definitions of the injectiveness, bijectiveness, surjectiveness, and we will go through them later, inshallah, in details. Okay, for the proposition that we will see right now, it's the proposition about the inversion. So if I'm in Rn and I want to go to Rm, I've succeeded in that too. Okay, I want to replace my movement going back from Rn into Rn. So linear transformation is such that from Rn into Rn is invertible. It can be invertible if and only if. It will happen if and only if n is equal to n. So I'm moving from R3 into R3, okay? Or from R2 into R2 and so on. So this linear transform will be applicable only if they are from the same dimension of these vectors. So R3 into R3, R2 into R2. A matrix AT is invertible. In that case, the linear transform matrix is equal to the inverse of the transform matrix. Or the linear transformation matrix, it has an inverse. Let's see. Here, let this transform move stuff from R3 into R3. How it's gonna move those stuff? If you have T, which is X, Y, and Z, it will be mapped into three components also. But the new three components, it's gonna be Y plus Z, then 2 of an X, a 4, and a Z. And that's for all X, Y, Z belongs to R cube. So if I want to have the linear transformation matrix, it's very, very simple. Either to write 0x plus y plus z, and for the second component, it's going to be 2x plus 0y plus 0z. For the third component, it's going to be 0x plus 0y plus 4 of z, or use the columns once more of a linear transform, as you can see, of a unit matrix. So I will substitute in this transformation by 1 double 0. It's going to be the first component 0, the second component is going to be 2, the third component is going to be 0. So it's a 0, 2, 0. Here we go. Here is the values. Use 0, 1, 0 once more on this transform. So it's going to be 1, it's going to be a 0 and 0. So it's going to be 1 double 0. Use the transform 0, 0, 1. So I will replace those numbers by 0, 0, 1. It will be replaced here too, same order. So it's going to be 1, 0, 4. And that's the transformation matrix in front of you. I want to check if this transformation matrix had an inverse or no, or this transform can be inverted or no. Once more, I can rewrite it in this manner if you like. Okay, then the inverse is, I'm trying to get the inverse of this matrix. We already in the previous chapters had the opportunity to know how to get in details an inverse for a 3 by 3 matrix using the unit matrix and playing with it. Then we will be able to get the inverse. We are very good in this at the time being. So that's the inverse of this matrix. Okay, if I want to check, of course, you are right. I can multiply elements by one, and I will get the unit matrix, of course, for multiplying AT in AT minus 1. Okay, which means, guys, that if T is invertible, the linear transformation T minus 1 will move back stuff from R3 into R3. And it is defined by, for T minus Y, the inverse transform is going to be this linear transformation multiplied in X, Y, and Z. So instead of having Y plus Z, it's going to be Y over 2. It's for the second component, instead of having 2x, it's going to be x minus z over 4. And for the last component, instead of having 4z, it's going to be z over 4. In this manner, this transform, it will move back stuff. Once more, to be sure that you understand me correctly, if this is R3 1 into R3 2, this is going to be the transform. If I want to move from R32 into R31, that's gonna be the transform or the function responsible about this transformation, as you would see, as you saw. By the idea, the exercises are really very simple. The first problem in the exercises is really very good. He's asking you to find the transformation matrix of the linear transforms defined by this is A, B, and C. And those are moving R3 into R2, R2 into R4, R4 into R4. All I have to do once more, for example, if I want to get the linear transformation for this transform, the linear transformation matrix, it's really very simple. As you can see, there is x1, x2, x3. So I will start 1x1 negative over 5x2 plus 4x3. So the coefficient matrix will be the first row 1, negative 5, and the 4. For the second row, I'm missing x1, so it's going to be 0x1 plus 1x2 plus negative 6x3. And the dimension of the linear transformation matrix is going to be 2 by 3 as we saw. Also, I can use the elements of a unit matrix. The elements of unit matrix will reform the values, but column by column. I will substitute by 1 double 0, then 1 0 1, then double 0 and 1. And similar for the rest of the transforms. Okay, that's a very interesting slide and a very important one too. Here in this linear transformation, or in this part, I want you to know that we can do a double transform actually. So I can say that T1 transform elements from Rn into Rb, and T2 transform from Rp into Rm. So I have two linear transforms, T1 and T2. T1 moving Rn into Rb, T2 move from Rb into Rm. The transform remark is very, very simple. The transformation matrix of the composition T2 composite T1, which means T2 of T1, is gonna equal to the transformation matrix of the first times the second. T2 times T1, if I am with this order. So let's see this example. This example is really very nice. We have the T transform, which moves from R3 into R2. And we have S that moves from R2 into R3. Okay, those linear transforms, their matrices are given. The one from R3 into R2 is already in front of us, which explained here. The one from R2 into R3, as you can see. So if I want to see the transforms, those are the transforms. If I want to get the transformation E composite S, all I have to do is to multiply the linear transformation matrix corresponding to the T transform times the transformation matrix relative to S. And this is what's happening here. This is the transformation matrix for T, and that's times the transformation matrix of S, and that's the result will be a 2 by 2. Remark how the movement is. It's moving from T3 from 3 into R2, then moving back from R2 into R3. Okay, for the transformation, S composite T, then we will use the linear transformation matrix stand for S times the linear transformation matrix stand for T, and in this case, S is moving R2 into R3, and it will map into R3. So mapping R3 as an input, and the result will be in R3 as you see. And that's the linear transformation matrix that we have. Okay, let's rock and go through the NumPy, the part of the Python with Colab. All you have to do is to try these two questions using Colab. Already you had an intro with Dr. Muhammad Saifuddin about the part of using Python. I want you to try these two programs together once more and explain the codes as you see. So here for the exercise, this is problem number 1 we just talked about. Here he wants you, I want you to exert an effort by trying to solve this exercise, and I will talk with you about it in the next session, inshallah. And we will do the assignment in campus together tomorrow, inshallah, at 2:30, bismillah. Here he is asking you to show that the transformation blue are not linear. So, and this is very, very simple. All I have to do is to remember that I have the two conditions for applying the two conditions, which is the distribution of the addition and the distribution of a constant time a vector for problem 4.2. For problem 4.3, and that's a very interesting problem, it's also standing on the T element, which is here. T, the transform, that's a linear transform. It's given to you. It's giving you in the data. Let's consider you have two linear transforms. That's T and G. So you have two linear transforms, T and G. And he's asking you, while you are using T and G, it's known that the T is given to you by inspection, by the values of the vector 110, which is going to map into 101. T of 100, which is gonna map into 102, T of 011, which is gonna map in 010, and then the G is giving you directly, explicitly. So the linear transformation for G, it's in front of you. It's really, very direct. It's for the first row, it's gonna be 100. For the second row, it's gonna be 2, 1, -1. For the third row, it's gonna be 0, 1, and 0. Of course, I can use 100 for the first column, 010 for the second, and 001 for the third. It will be obvious to have, or it will be very easy to have this transformation matrix. Okay, the T has tiny trick that depend on this relation. Remark the given vector, the first vector, which is u, for example, this 1 plus 0, it can be considered as 100 plus 010, which means u and v. The u will be 100, the v will be 01 and 0. And the transform of both of them is given, which is 101. The transform of 100 is given, which is 10t. 102, I'm sorry. From here, I can get the transform of V. If you have the transform of V, I will do exactly the same for this guy here. T of 011 is equal to T of 010 and 001. You already have the values of 010 from the previous step, so you can get the remaining, which is 0, 0, and 1. And so you have the columns of the transformation matrix in front of you. So that's the first requirement, which you will get from the first movement. This is to help you. A transform will be given, and he is asking you, is the inverse of T? Once you have the linear transformation matrix of T and you have the linear transformation matrix of G, multiply them together, and it will equal to the unit matrix. Please try to exert some efforts. You have the composition down. I will leave this question for you, and the other two questions after that. Also, I will leave them to you to think about, and we will discuss them in the next lecture, inshallah. After this lecture, I will send you the slides completed in order to help you out with the rest of your work. Okay, here is the exercises, as I told you. Here's also for the true or false. He's asking you, there are linear transformation from R4 into R2, such that the different objects necessarily correspond different images. Yes, so the answer will be, as I told you. There is no linear transformation T that transform the vectors 110, 101, and into the vectors 100, 010, 001, respectively. Try to go through them, and you will have your answers in front of you. I've written the answers for you all. Thank you very much. I'm very happy to be with you today, and I hope this lecture is good for you. please try to go through the previous lecture first and then go through this lecture, and you